Hello everyone and welcome to this presentation. Today I'm excited to introduce our research titled End-to-End Automation Learning for Unsupervised Log Anomaly Detection. This work focuses on developing an automated machine learning framework for detecting anomalies in logs without the need for label data. And our approach aims to simplify the log anomaly detection process by automating both feature extraction and module selection. Our project is a collaborative effort between several institutions, including Nankai University, the Chinese Academy of Sciences, and Microsoft, as shown here at the bottom. Over the next few minutes, I will walk you through the motivations, design, and the results of our framework, and let's get started. System stability is essential for modern software systems. When an issue occurs, it can lead to distributions and negative user experiences. Logs are a crucial tool in diagnosing these problems. By analyzing logs, we can identify the root causes of log system failures and implement effective solutions, ultimately restoring stability and improving user satisfaction. And first, let me introduce the basic workflow of log anomaly detection. This workflow can be divided into four main steps, including log parsing, log grouping, log representation, and anomaly detection. In log parsing phase, we need to convert raw logs into structured in-log information. By parsing, we extract the key events from the logs, making subsequent analysis more convenient. Next is log grouping. In this step, we need to group log events based on specific window. Common grouping methods include sliding windows, fixed windows, or extension windows. And third step is log representation, where the grouped logs are converted into vector representations that can be used for machine learning models. The final step is anomaly detection. At this stage, we use various machine learning algorithms to analyze the logs, like clustering, next token prediction, and classification. Let's talk about log representation. Logs can be transformed into different types of vectors to help us analyze and select anomalies. And this brings us to a quick question. Which type feature performs better for anomaly detection? Should we focus on a sequence, the quantity, and or the semantics, or perhaps a combination of these features? Next, let's move to anomaly detection techniques. A critical challenge we face is how should we select the right anomaly detection method for a given dataset? And equally important, how should we determine the best hyperparameters for these methods to ensure optimal performance? Our goal is to automate the end-to-end process of anomaly detection, covering four critical stages like log parsing, presentation, model selection, and train and inference. However, there are some notable challenges. One of the biggest obstacles is that diversified datasets present significant challenges for future engineering. The quality of template extraction and the log representation methods we choose greatly impact the final anomaly detection results. Another major challenge is dealing with the sheer number of parameter combinations and the prevalence of unlabeled data. This creates hurdles in both model selection and evaluation. Each module has numerous hyperparameters, and model evaluation needs labeled data, making performance assessment difficult with unlabeled data. Next, I will explain how we design LogCraft to achieve our goals. The framework of LogCraft is divided into three main modules: adaptive feature enhancement, meta-learner construction, and model preparation and detection. To address challenge one, we employed a combination of semantic analysis and clustering techniques to enhance the accuracy of template parsing. By leveraging these advanced methods, we can better understand and categorize the data, leading to more precise parsing results. Additionally, we will incorporate filter combinations as part of the candidate site filters, providing a more robust framework for identifying the most relevant patterns and improving overall system performance. To address challenge 2, we designed a meta filter extractor and combine it with collaborative filtering techniques to recommend modules from the candidate site for unlabeled datasets. Traditional log parsing has some clear challenges. For example, we often deal with inconsistent variable lengths. There's usually a lack of filtering rules, and most importantly, semantic information is often neglected. Rather than manually crafting expressions, we could leverage automated methods, like sentence vector encoding and clustering. This way, we capture the semantic meaning of the logs without needing to hardcode every pattern. As you can see at the bottom, the process starts with raw logs, goes through parsing, embedding, and finally clustering, resulting in a structured log output. This gives us more flexibility and consistency in handling diverse log data. Another challenge we face is that different datasets have distinct characteristics, making it difficult to consistently identify key anomaly features. The variability across logs means that features important for one dataset may not be as relevant for another. To address this, we propose incorporating feature combinations into the model's hyperparameters. This approach allows us to explore and evaluate multiple combinations of features, ensuring that we capture the most relevant characteristics for anomaly detection across diverse logs. The process begins with extracting feature vectors from the data, which are then combined in different ways, such as using sequential, semantic, and quantitative vectors. These combinations are fed into a pool of candidate modules, allowing us to optimize and select the best performing module for accurate anomaly detection. To select a well-performing module for unlabeled log datasets, the results of the modules on existing datasets are used for recommendation. Two factors are essential: performance evaluation and similarity measurement. We selected four base algorithms and combined them with different parameters to establish a candidate set containing tens of millions of modules. Next, we run the particle swarm optimization algorithm on four labeled datasets, retaining potential candidates and recording their performance as a performance matrix. Then we designed a meta-filter extractor specifically for log data. This extractor generates fixed-length vectors to represent log datasets. The process involves two types of meta-filters: statistical meta-filters and model-based meta-filters. For statistical filters, we apply matrix analysis to the filter vectors. This involves calculating metrics like variance and kurtosis to capture the distribution properties of the data. For model-based filters, we use methods such as clustering and isolation forest. From these methods, we extract intermediate results, such as intercluster distances, which are then included as part of the filter vectors. The result is a meta-filter matrix that condenses important information from the log data into a usable form for further machine learning applications. And the goal of the meta-learner is to learn a regression function and a new matrix referred to as a learner matrix, such that the dot product of the meta-filter matrix after a linear transformation with this matrix approximates the performance matrix. When new log data arrives, it is structured and associated with meta-future extraction. The resulting meta-future vector undergoes a linear transformation and is multiplied by the learner matrix, resulting in the performance vector. Each column of the vector represents the estimated performance of the corresponding module on the dataset. Next, we'll discuss the experimental evaluation of LogCraft. We designed LogCraft using 5 publicly available datasets: HDFS, BGL, Thunderbird, Spirit, and Liberty. For the Thunderbird, Spirit, and Liberty datasets, we limited the evaluation to the first 5 million entries due to the large size of these datasets. To evaluate the effectiveness of LogCraft, we designed 3 research questions. Q1, how effective is LogCraft in unsupervised log anomaly detection? Q2, how effective are the key components of LogCraft? And Q3, how do parameter settings impact the performance of LogCraft? And for Q1, we compared the performance of LogCraft with 6 unsupervised log anomaly detection baselines, including PCA, IM, DeepLog, log anomaly, CNN, and LogBert. LogBert consistently delivers superior or competitive results. Its balanced performance between precision and recall makes it a highly reliable solution for log anomaly detection. And for Q2 is the application experiments for LogFE. We first tested the effect of removing the task of merging template semantics and directly extracting future vectors for module training. And we find that after template merging, the model's performance improved across all datasets, and the detection speed increased on 4 datasets. In the ablation study experiments for LogFE, then we attempted to train and detect the module using only one certain features to verify the improvement in the performance. And LogCraft either matched or exceeded that of the single future module across all datasets. And for the meta-future learner, we compared the performance of LogCraft with other recommendation algorithms. LogCraft outperformed other recommendation algorithms on 4 datasets and achieved the theoretical optimal value on 3 datasets. And although LogCraft is designed as a black box, the operator can still influence the model's performance by modifying the similarity threshold for template merging, and we evaluated LogCraft performance under different hyperparameter settings. And we finally cited the STH as 0.19 in our paper. The following are the conclusions we reached in our work. First, log data representation is crucial. Since different logs exhibit varying patterns, choosing an appropriate representation for them is essential. It significantly impacts the result of anomaly detection tasks. Second, meta-futures enhanced log analytics. Meta-futures can be seen as an abstract representation of log datasets. Designing appropriate meta-future representations for large-scale datasets can help us gain deeper insights into the data. And in conclusion, this paper introduces LogCraft end-to-end unsupervised log anomaly detection framework based on auto machine learning. LogCraft shows good performance on 5 public datasets with an average FN score of 0.899, surpassing existing unsupervised detection anomalies algorithms. LogCraft represents the initial effort to derive fixed dimensional vectors as latent future representations from an entire log dataset. The meta-future extractor we propose also demonstrates significant promise for sizing dataset similarity and advancing research in the field of log analytics. Thank you for your time and attention. I'm very happy to take any questions or discuss the work further. Your feedback will be greatly appreciated.